Okay, so in this video, we will sketch the graph of the following function. And of course, we will need, in order to do this, we will need to find the first and second derivative. And, as always, we will try if we can to find the zeros of the function, and we will also need to find the zeros of the first and second derivative to find, if any, the critical points and possible inflection points. Can we find the zeros? So, if you try and find a way to factor this polynomial, you will have a very, very difficult time. So here, as it is too difficult to factor the initial function, we simply give up on finding the zeros. Let's skip now the first derivative and factor the easier second derivative. We have an obvious common factor of 12 and also of x. So we can factor from the whole thing 12x. Then we're left with a single x in the first case and a 2 in the second. So we now have the second derivative fully factored. What about the first derivative? Well, this one will be a little bit more interesting as it is not a quadratic but a cubic polynomial, but we can at least factor a multiple of 4. Now what? Well, it's not clear how to factor this polynomial as it is again a cubic, not a quadratic polynomial, but we can think of using, if we can, the zero theorem. Instead of looking for a factor of this polynomial, can we find by inspection a zero? And if you look at the coefficients, 1, 3, and negative 4, it should be clear that if we plug in x equals 1, the result is 1 plus 3, 4 minus 4 is 0. So because 1 is a 0 of the polynomial, automatically x minus 1 will have to be a factor of this polynomial. And you can find the missing factor, which will be a quadratic factor, by long division. And this I will leave up to you. Using long division, divide the polynomial by x minus 1, you will find a quadratic factor. And again, that one you can easily factor with the product sum trick. And what you will find is that it factors as x plus 2 times x plus 2, therefore x plus 2 squared. So now we're good to go. So we've just said before, since it is too difficult to find a factoring of the initial polynomial, and you can try by inspection to look for a 0, and you will not find one, so we give up on the zeros, and we jump right away to the y-intercept. The point at which the function crosses the y-axis, therefore the y-value of the function at 0. So we plug in here x equals 0. The result is obviously 2. Now we look for the critical points. Points where the derivative is 0 or undefined. Well, as the derivative is a polynomial, it never is undefined. So we only have critical points possibly of type 1 when the first derivative is equal to 0. And again, from the factoring, this is trivial. This can only be 0 if x is 1 or negative 2. So we have 2 critical points. What about possible inflection points where the second derivative is 0 or undefined? Again, the second derivative is a polynomial. It always is defined. So we can only have here inflection points or possible inflection points of type 1 where the second derivative is equal to 0. And again, as we have a complete factoring of the second derivative, this is clearly 0 if x is 0 or negative 2. So we have 2 possible inflection points. And what's interesting when you look at the critical and possible inflection points is negative 2 is both a critical point and a possible inflection point. Now, as always, the next step will be to try and figure out what does the function look like around the two critical points. Therefore, we have to classify those two critical points. So let's include two distinct x-axes, one for each critical point. So 1 and -2. And as always, we will need to evaluate the second derivative at each critical point to figure out if the curve is concave up or concave down. But first recall that both were critical points where the derivative was 0. So at each critical point 1 and -2, as the derivative was 0, the curve was flat there. So we have a horizontal tangent line. And now, of course, we have to figure out, is the curve concave up or concave down? Now, of course, this is a bit slanted, but it should be perfectly horizontal. So let's evaluate our second derivative at 1. And again, we don't need the exact value, just a sign. Will this be positive or negative? So plug in here x equals 1, we get 12 times 3, so 36, but we don't care. The result is positive. So at x equals 1, the curve is flat and concave up. So we have therefore at 1 a local minimum. What about -2? Well, again, we ask for concavity at -2. And if we plug in x equals -2 in the second derivative, we get -24, but times 0. And so the value of our second derivative at -2 at our second critical point is equal to 0. So the classification at -2 fails. When the second derivative is 0, we do not know if the curve is concave up or concave down. But this is not a big problem. We are still left with the same question. On either side of our critical point, is the curve concave up or concave down? As the classification fails at -2, we simply have to look a little to the right and a little to the left of -2. So we can pick on the right, negative, say, 1.9. On the left, -2.1. So let's evaluate the second derivative at those 2 points. And again, we do not need the exact value of the second derivative at either point, simply the sign. Will it be positive, therefore concave up, or negative, concave down? So let's plug in -2.1 in the second derivative. We get here 12 times -2.1, that's negative. -2.1 plus 2 is -0.1. So we have a negative times a negative, therefore the result is positive. So on the left of -2, the curve is concave up. And at -2 it is flat, so it has to look like this. Now on the right, at -1.9, well, again, this will be -1.9 times 12, that's negative. But -1.9 plus 2 is 0.1, this is positive. Now we have a positive times a negative. The result is therefore negative. So on the right of -2, the curve is concave down, but again is flat at -2. So there's only one option. The function must look like this. And now we have a complete classification of our critical points, -2 and 1. So all that's left now is to find, for each interesting x value, the corresponding y value, so that we can then sketch the function accurately in the xy plane. So we construct our table of values. And there weren't that many interesting x values. There was no easy zeros to be found, so we gave up on those. We have the y-intercept, of course, when x is 0. Then we have, x equals 1 as a critical point, then x equals negative 2 as the other critical point, and 0 was also a possible inflection point, we already have it, and negative 2 was also a possible inflection point, and we already have it. So we only need to find 3 distinct y values. So let's look at the original function, replacing in each case x by the appropriate value. So when x is 0, y is clearly 2. When x is 1, we get 1 plus 4, 5, plus 2, 7, minus 16, negative 9. And finally negative 2, so you'll get positive 16. Then negative 8 times 4 is negative 32, so that's negative 16. But then positive 32, negative 16 is positive 16 plus 2, positive 18. So we now have the 3 corresponding y values. So let's include those in the xy plane. And as there's a pretty big difference in the range of x values and in the range of y values, we will use different scales for the x and the y axis. So of course this means that we will have a slightly distorted picture of the function, but it will still be fairly decent. So on the x-axis, we have a range between negative 2 and 1, so we will go in steps of 1. So 1, 2, 3, negative 1, negative 2, negative 3. And along the y-axis, we have a much larger range of y values. So the larger one is 18, the smaller one is negative 9, so we will go here in steps of 9. So let's say this is positive 9, then positive 18, then negative 9. And now let's include our 3 points, so that we have the point x equals 0, y equals 2. Then the point x equals 1, y equals negative 9. And finally, x is negative 2, y is positive 18. So we have those 3 key points. And let's now include the classification of our 2 critical points in the graph of the function. At 1, we have a local minimum. So at 1, the function will have to look like this. Flat there and concave up. Then we had a slightly more interesting critical point at negative 2, where there is a change in concavity from concave up on the left to down on the right. But at negative 2, the curve is flat. So let's paste this onto the point x equals negative 2. And then let's see, what was the point now? If we look between negative 2 and 1, the only other point of interest was 0, 2. And this point, if you recall, was a possible, x equals 0, was a possible inflection point. So concavity could change at this point. Does it? Well, let's see. On the left of this point, the curve is concave down, but on the right of the point, the curve is concave up. So indeed, the curve does change from concave down to concave up. And again, a curve can only change concavity at a possible inflection point, at a point where the second derivative is 0 or undefined, and x equals 0 is such a point. So concavity will have to change exactly at this point. So the curve will be concave. So here I'll have to correct my course a little bit. I'll make the curve a little flatter. So the curve must be concave down, decreasing until it hits the point x equals 0. So then this will have to be removed. And then the curve, as soon as we go past x equals 0, shifts from concave down to concave up. And if you go now look past x equals 1, there is no other critical or inflection point. So as the curve is increasing concave up, it will be increasing concave up forever. And on the left of negative 2, there is also no other critical or inflection point. So as the curve is decreasing concave up, it will remain like this forever. So here this is a bit too exaggerated. Let's try and make it look a little smoother. And again, the only question that remains, are there possible horizontal asymptotes on the right and on the left of the function? So let's look at both corresponding limits. Limit of y as x tends to positive infinity. The function, if you recall, was x4 plus 4x3, negative 16x plus 2. And again, as x tends to infinity, the first three terms, so these two go to positive infinity, but then this one goes to negative infinity. So this may seem like a tricky limit, but as x becomes larger and larger, by far the larger term is x4. So we simply have to factor x4 from the polynomial. What's left over is 1 plus 4 over x, negative 16 over x cubed, plus 2 over x4. And now if we check our case, the limit becomes trivial. As x tends to infinity, x4 tends to infinity, times, as x tends to infinity, 4 over x, 16 over x cubed, and 2 over x4 all go to 0. So we're left with times 1. So of course the limit is equal to positive infinity. So as x becomes larger and larger and positive, y also becomes larger and larger and positive. So as we move towards the right along the x-axis, y will also shoot up to positive infinity and always concave up. Now on the left, we ask the same question, but as x tends to negative infinity. And I will leave this step up to you, as it is the exact same step. We will factor x4, and the case will now, as x tends to negative infinity, as 4 is even, this will also tend to positive infinity, as an even power of a negative is positive. And as x tends to negative infinity, these three terms will also shrink to 0, so this will be approaching 1. And the limit is once again positive infinity. So as x gets larger and larger and negative, y shoots up to positive infinity. So it keeps increasing forever. So it's clear that we have no horizontal asymptotes on the right or on the left. So we now have a fairly accurate sketch of the function. The function is decreasing concave up. Then we hit the critical and inflection point x is negative 2. Then the curve shifts from concave up to concave down, but remains decreasing. We hit the other inflection point x equals 0. The curve keeps decreasing but shifts to concave up. Then we hit the critical point x equals 1, where the function attains a local minimum. It is always concave up, but now shifts to increasing and goes increasing concave up to infinity forever. So let's label now the three key points of this function. So this critical point was neither a local max or min, but it was an inflection point. x equals 0 was also an inflection point. The curve goes from concave down to then concave up. And x equals 1 was a local minimum, but notice something interesting. If you look at the full sketch of the function, x equals 1 is not only a local minimum, it is a global minimum. At no other point on the x-axis does the function attain a smaller y value than negative 9. So x equals 1 deserves the term global minimum. And that's it.